All right, well, here we are on our third day. I had a little technical disaster for the last lecture. For those of you who are looking at this online, I completely lost the demo dialogue from yesterday's, or from the last time we met. So I'm going to have to do it offline. I'm sorry it will not be quite as spontaneous as the one we did. So you guys who are here in person got the real deal. Anyway, so this is also our first day that an assignment is due, right? So how'd it go? I don't remember exactly what. Do you have a question? Yeah. Oh, it went good. Okay. Any others? What were the problems? There was like a tax problem and a cooking recipe, candy temperature.
And then the quilts, like the quarter turn.
Oh yeah, yeah. Oh, so this was the one where you make the pinwheel. Yeah. Did that work good?
Mm-hmm. Yeah.
Yeah. Okay, good.
That was fun.
Oh, you're showing me your pinwheel. Oh, yeah. All right, good. Yeah, question?
So this homework is due at midnight?
Yeah, actually, it's 11:55 is when I set it on the course's webpage. So yeah, it's all electronic. Remember to pre-pin your two-digit assigned number to you, the name of the file. Okay, and then it's what's the file extension? .rkt, right?
Yeah.
Yeah. And so everyone's up and running fine. Everyone's good? We're all got Dr. Racket. We're programming in Scheme. Excellente. Okay, at the end of class last time, I think we were, I think we had done this. Didn't we write the factorial function last time? I thought we wrote the factorial function. Didn't we write it? Because didn't we run? I don't know, but didn't we run it with all those big numbers?
Oh yeah, we did.
We did. I remember because we did 50 and there was all those numbers. Remember? Okay, yeah. So we did do the factor. We wrote the factorial last time. So now let's do another one. Let's do one. Let's do one to compute the square. Okay. So here's what we want to do. We want to square a number recursively without doing multiplication. Think about that a minute. We want to square a number recursively without doing multiplication. Now, let's go back to our recursive definition of factorial. You know, how does this definition work? It defines n factorial to be 1 in the base case, but to be n times n minus 1 factorial. So this is n factorial defined in terms of n minus 1 factorial. So in order to square a number recursively without multiplication, what do we have to have? What kind of an expression do we have to have? We have to have n squared. How? The definition of n squared. Let's go back. What do we have? What's this definition of n factorial? N factorial in terms of n minus 1 factorial. So if we're going to square recursively without multiplication, what do we have to do? Have what?
N minus 1 squared.
Yeah. Define n squared. How? In terms of n minus 1 squared. So can you think of a recursive relationship? Can you think of the relationship? How is n squared related to n minus 1 squared? Can you think of a way that would work? You know, here n factorial is n times n minus 1. What do we need? We need n squared equals a base case and then what? Something with what? n minus 1 squared. How could you do that? It's actually not difficult at all. It's just a little algebra. Well, look. We need to compute n squared given n minus 1 squared, right? So look at there. What do you think you should do? What do you think we should do? Can we multiply n minus 1 squared out? Can we multiply it out? And what do we get? No, n minus 1 quantity squared. What do we get? Ah, okay, so n minus 1 squared is what? N squared minus 2n plus 1. This is really high math. And so therefore, what?
We have n squared.
But no, we want n squared in terms of n minus 1 squared. So what do we have? So what does n squared equal?
Oh, n minus 1 squared plus 2n.
N minus 1. There it is. Are you with me? And furthermore, so do you see then that n squared is, here we have n squared in terms of n minus 1 squared. So what we can do is we can write a recursive function to square n, and this n minus 1 squared will be what in scheme? That will be our recursive call. But it's not this times n. What is it? It's instead of times n, what is it? It's what? Plus 2 times n. But we want to do it without multiplication. But that's easy because what's another way to write 2 times n without multiplication? N plus n, and then minus 1. And there you have it. So let's do it. You got your scheme? You got your Dr. Racket up? Can we do this? Can we figure out how to do this? Using what we know about scheme? Okay, so let's try. What we want to have happen is, see if we do square 5 here, I think it doesn't work, right? Or does it? Does it have square in it?
I don't think so.
Yeah, it's undefined. Okay. Okay, so let's define, so now how do I define square? What's the first, can you tell me what to type here? Parentheses. Yeah, okay, next. Define and square. And then, what do we always put here? Like this? Oh, parentheses. Lambda. And then what always goes here? Parentheses, and then we'll say n just for fun. Okay? We could call it anything we want. Is this the actual parameter or the formal parameter? Formal, because we're defining it, the function, right? Okay? And now, how do you always do a recursive function? What do you always check for first? Usually check for first? The base case. And what is the base case? Yeah, if we go back to the, yeah, so that's the recursive case, but then what the base case would be 0. I think that's good. Okay. So here, so it would be, so now how do we check for that in scheme, in Lisp? Parentheses, if, and now what? Yeah, but why not use 0? That gives us a little bit more range. Are you with me? Why not have it work for 0 also when you can? So why limit ourselves? All right, so if what? N equals 1 or n equals 0? No. Parentheses equals n 0 parentheses. All right, so now if equals n 0, what do we know the square is? Yeah. Okay. Well, now what goes next? Here, let's go back to the slide. No. No, because, yeah, the question is, aren't you going to still use multiplication because we're doing squaring n minus 1? We're not going to square n minus 1 because that n minus 1 is going to be a function call, and that is going to call itself recursively again, which is going to call itself recursively again, and it's never multiplied by itself. Are you with me? So as it calls itself, it'll get smaller and smaller and smaller, and then it'll unwind. Yeah? Okay, so, but now what do we have to do? So here, what do we have to do here? What is this whole, what do we have to return in this recursive case? Right. I guess we can do this. I guess there's several ways we can do it. Let's add the n minus 1 squared to the rest. Are you with me? So the first thing that we'll do here, let's go back to Dr. Racket. So here, let's do, so what do I have to put here?
n+1.
No, you can't start with n because n's not a function.
Plus.
Are you with me? You got to do plus. The function, are you with me? The function always has to come right after the paren. Okay, so what are we adding? We are adding, now let's do the recursive call. It's parentheses. So now how do we do the recursive call?
Square.
S-Q-U-A-R-E, square, and now it's, what is it, n-1? So do we say n-1? No, it's parentheses minus
N.
n1, boom. And now I need another paren, right? Boom. And now what am I adding to that?
N. You're gonna add n plus 1.
So I'm going to put that on the next line. So we're adding that, well,
Parentheses.
yeah, but, yes, parentheses. But now what are we doing? Let's go back to here. Now I think what we should do is this. Now what I think we should do is this. Now what are we doing?
The last part.
We already have the plus. But what are we adding?
N.
2n minus 1. So what do we have to do? Yeah, we're going from infix to prefix here. Come on, you guys. Well, look, there's the, it's 2n, we have to add 2n minus 1. So what do we have to add?
N minus 1.
Well, we have to minus
N plus n and 1.
n plus n and 1. Yeah, yeah. Is everybody with me on this? We have to minus n plus, everybody good? Okay, so let's go back to here. So this is going to be, minus, and then now we do the addition. Parentheses what? Plus n parentheses and what? 1. Is that right? Close it out, close it out, close it out, close it out, close it out. I think so. Let's run. Well, didn't have any syntax errors there. So now let's try it. Square 5. Oh, just to show that it was not a coincidence. Square 6. And just to test the base case, square 0. Yeah? Are we good? Does everybody see how that, are we good with that? Okay, now, the next thing we're going to do is something that we're going to do several times in this paradigm, and it's a really important thing to be able to do. What we're going to do is, what we want to do now is we want to prove that that program is correct. Yeah, question? No, 0 squared is 0. 0 factorial. You were thinking 0 factorial. Yeah.
Yeah.
Are we good? Okay, so is everybody with me? Now what we want to do is we want to prove that this is correct. So look, anytime you want to, so we're going to reprogram that in Scheme. So this is our task. So here's what we wrote in Scheme. And we want to prove that this program is correct. Now, you guys, what proof technique do you think we're going to use to prove that this program is correct?
Mathematical induction.
Probably. Now, not just probably, yes. We are going to use proof by mathematical induction. Now, why is it, so here, the correctness proof of a recursive function is by mathematical induction. Now, why do you suppose that recursive programs are proved by mathematical induction. Because in a recursive program, what do you have? You have the what? What case?
Base case.
You kind of like you got the base case, and then you have the recursive, the induction case. And in proof by mathematical induction, what do you have? The base case. And so, are you with me? So it's really important that and so therefore there's a really natural correspondence between recursive algorithms and proofs that those recursive algorithms are correct. So, so we're going to use mathematical induction. So the base case in the mathematical induction corresponds to the base case in the code, and the inductive case corresponds to the recursive call in the code. So, there's that connection. And now here's the thing that we have to do. There's one more thing that we use. There's one more kind of like technique that we use to link the program to the proof by mathematical induction. And we're going to call this code inspection. All right? So what we do is we use code inspection to convert from scheme to traditional infix notation. And we're going to do that both in the base case and in the inductive case. So does everybody kind of like see the general overall idea? So in proof by mathematical induction, what you do is you prove the base case, and then you prove the inductive case. And when you prove the inductive case, do you remember you always have to formulate the what? The what hypothesis? The inductive hypothesis. So we're going to have to do that. All right? So let's see how we would do that in this particular example. Okay, so check it out. Here's the code. Define square lambda n if equals n 0, 0, otherwise plus square minus n1 minus plus n1. Okay? Now, we're trying to prove, now here's kind of like the main idea. We're trying to prove that this is correct, right? So what two things have to correspond? The program on the one hand and math on the other. Are you with me? So the proof consists of showing that the program results match the math results. Is everybody with me on this? Okay? So here's what we do. First of all, we take a look at the program, all right? Now in the base case, remember we said we were going to use code inspection. In the base case, what happens is we do code inspection. And what is the base case? What's the value? Actually, you said we could have used the value of n, but we used the value of n. We could have used the value of 1 for n. We decided to use the value of 0. So the base case is n equals 0. So we just inspect the code. And what do we see? If equals n 0, what does it do? What does the code do? It returns 0. So that's the code part. But now what do we have to state to prove the base case? That was the program part. What was the other part? We have to show that that corresponds to what? Come on, you guys.
Base case.
When n equals 0.
Yeah, but what were the two parts? Okay, let's go
The
back.
base case is the code.
We have to show, no. What were the two, what has to correspond? Math.
0 squared equals 0.
That's the point. It seems trivial, but that's the point. The second point is, by math, 0 squared is 0. And so we see that because this returns 0, and by math it should be 0, that program is correct in the base case. Are you with me on this? It's trivial, but the reasoning is what's important. Are you with me on this? Because look, what we have on the one hand is a programming construct, and on the other hand we know mathematically what it should do. So we have to compare what the program does with what the math says it should do. Yeah? Is everybody clear about that? Okay, so that's the base case. So therefore, because it returns 0 and because the math says it should be 0, therefore it's correct in the base case. Yeah, question?
Does this program, this definition of the short only works with integers?
Yes.
Okay.
It does only work for integers. That was an unstated assumption. Because otherwise, if it were 0.5, it would never equal 0, and the recursion would go on forever. Yeah, that's a good point. Okay? And now, now the next part is a little trickier. It's the inductive case. All right? Now, anytime we have the inductive case, what do we always have to say? Remember, we always say it the same way each time. In the inductive case, what do we have to say? We have to say, must prove what, assuming what. All right, you remember how we have to set that up? So what is it that we have to do? I'll give you the first one here, the first part of it. Prove that square n terminates with the mathematical value n squared. That's what we have to prove. But what's the second half of the sentence? Always. Assuming something as the inductive hypothesis. So can you tell me from this what the inductive hypothesis is?
Assuming that square n minus 1, or whatever it would be in scheme, terminates with the value n minus 1 squared.
Yes. But let's do it in scheme. So say it in scheme. Square, parentheses, minus n1 terminates with n minus 1 squared. That's correct. So assuming that square minus n1 terminates with value n minus 1 squared as the inductive hypothesis. All right, is everybody clear? Yeah, I don't have these slides posted yet, but I will once I get chapter 2 done, or maybe before.
It's going to be posted.
Yeah, it will be. In that case, why expend all that energy? But sometimes it's good sometimes you can remember better when you write it down. So that's good too. All right, so now we haven't done it yet. This is what we have to prove, and this is how we assume it. So what do you suppose we should start with?
The code inspection.
Yeah, that's going to be our yes, that is going to be our very first step. But the thing that we want to prove is that we want to show that we have to prove that this square n terminates with this value. So let's start with what square n returns. Let's start with the value that square n returns. And then code inspection will be our first step. Do you see what I mean? So here's how we're going to do it. The inductive case, we're going to lay out the inductive case like this. Okay? The value returned by square n. All right, now you guys, equals. In the end, what do we have to get at the bottom? We have to get n squared, right? Because that's what we had to prove. Is everybody with me on this? See, we're going to start with the, and we have to get with what? So we're starting with what square n returns, and we got to get it to be n squared. So so the value returned by square n. So now what's the first step? What do you suppose the first step is? Actually, we mentioned it a minute ago. Code inspection. Okay, so equals by code inspection. Is everybody good with this so far? Well, schemers, inspect the code and tell me what it returns. Can you inspect the code and tell me what it returns? I mean, there's the code up there, so what does it return?
Square.
The square of minus n1, and then what?
Plus.
Plus n plus, well,
Do we get
n, no, let's not evaluate yet. Plus, let's do it, let's just translate to here. The idea here is we're going to translate this to the traditional infix so that we can manipulate it. So let's translate that to the traditional infix. So what do we have?
Square n minus
Square minus n1, okay,
plus
and then what?
n plus n minus 1.
Plus n plus n, yes, minus 1. Now, is everybody good with this? But now what? Yeah, look, now we can go back to the what? Assuming that what? Because that is our inductive hypothesis. Are you with me? So that means on this step over here, what's that? We can say equals by the what?
Inductive.
Yes. Is everybody good? Equals by the inductive hypothesis, what?
Just the right side left.
Well, I mean, it's just this. We have to bring this one down.
N minus
But we know by the inductive hypothesis what this does. Are you with me? So this is what?
n minus 1 squared.
Yes, n minus 1 squared plus, and then we bring that down. And now what?
Math.
But now by math, we can do what? Let's do ahead. So what's n minus 1 quantity squared? Plus n squared plus what?
Or plus 2n
Minus 1. And what's n plus n?
2n.
2n. So that's n squared minus 2n plus 1 plus 2n minus 1. And now what?
Math.
Equals by math what?
The answer.
N squared and boom boom. Well, I mean, that's the way I do it on my LaTeX. But anyway, does everybody see how that proof works? Okay. So in general, that's the general way to do it. That's the general way to prove that a recursive algorithm is correct. Is if it's correct, then you have some standard that it is some standard that you know mathematically that it has to be correct for, and then you formulate the base case. And for the base case, you inspect the code and you make sure that that works for what you would expect, mathematically. And then you formulate your inductive hypothesis. And then after you formulate your inductive, you state what you're trying to prove, assuming the inductive hypothesis. And then you go through, and again, the first step is code inspection. Yeah, you the value returned by, and you code inspect and say, okay, how are we doing? Is that good? All right. Now, let's do, so we got the square to work, we demoed it, and it's good. Okay, so let's go to Dr. Rackett again and do some more scheming. Okay, now check this out, you guys. There is a built-in function called quotient. See if you can see what quotient is. Here's quotient 9.3. Anyone want to predict that? Yeah, and how about quotient 10.3? Anyone want to predict that? Yeah. How about quotient 11? Oh, key. How about quotient 11.3? Still 3, but now's your chance. Quotient 12.3, what's that? 5. Dang. Okay, so everybody understands what quotient is. But now, but what about this? That's not defined, right? So let's define it. Let's define our own QUOT that does the same thing that quotient does. Now, does anybody have any ideas on how we're going to do this? Because look, here's where it's going to start. It's going to start with define what? What do we call it? QUOT. What's our little abbreviation? Our little abbreviated one. Define quote. Okay, And now, what two things did it, here, the same thing as quotient. Let's do quotient 11, 3. So now, you know, we have more than one parameter. Did your homework have a thing with more than one parameter? Okay, good. So lambda. So now let's call it lambda ND. Okay, now, how are we going to do this? Oh, guess what? You ask such good questions. Guess what in scheme?
No loops?
There are no loops.
Okay.
There are no loops, and pure functional programming has no loops. It's related. Remember we had that question the other day? We said, well, wait a minute, what about a function that changes the value of error? And what did we say yesterday, or last time we met? What did we say last time we met about call by reference? What did we say about call by reference in scheme, in Lisp? In pure functional program, there is no call by reference. Everything is called by value. And guess what? In pure functional programming, what? There's no loops. Instead, all repetition is done by what? Recursion. Hoo-hoo! Pure functional programming.
Can we write a recursive function that makes it so you can use loops?
What do you mean makes it so you can? You mean that like? Actually, you're asking some very good questions, and we're actually going to answer that question, a variation of that question, pretty soon now.
Okay.
Maybe even tomorrow. Maybe even tomorrow we might actually work on that question. But yeah, how are we going to do this this quote, right? How are we going to lambda ND? Because we don't. Here, tell me what is down here we had this example, quote 11.3. So here, what is quote 11.3? I mean, let's look at it this way. Let me ask you this. What did we say? Let me ask you this. Let's do this. Let's do quote. Let's do quote 4.3. What's quote 4.3? 1. And then what about quote 3.3? 1. And what about quote 2.3? 0. And what about quote 1.3? 0. And what about quote 0.3? So what does it look like, you guys? What does it look like? Because when you have a recursive function, what do you always have to have? A what?
Base case.
Well, so what do you think? Yeah, you have to have a base case. So what do you think?
If n is less than d,
Yeah, and this 4 is the n. Is that right? Is that what we called it? N, yeah. This 4 is the n, and this 3 is the d. So what'd you say?
if n is less than d,
Yeah. Right here, n is less than d, yeah? And so if n is less than d, that's the 0, and so this is the base case, right? Is everybody good? is the base case. And now I ask you, what is quote 11.3? Because is 11 less than 3? Is 11 less than 3, yes or no?
No.
No. So this is not the base case. But if it's not the base case, what is it the same as? What is it the same as? What do we have to do? When we make a recursive call, we have to do it for a little bit less. I mean, we have to do it for a smaller problem, right? We have to get closer and closer to the base case. For the base case, what do we have? Aha! Who said that? Yeah. So quote 11.3 is the same as, it's the same as what? Same as what? In this particular example, it's the same as what? Quote what? 8.3. Oh, plus 1?
Because you just subtract 3 from
8.3 would be 2.
No, isn't it the same as the 8.3?
The answer would be different.
Will it?
Yeah.
8.3 is
Oh, you're right. It's this
Plus 1.
plus 1. It's 1. Yeah, it's this plus 1. Oh, right, because we subtracted 3 from it, so it's 1 more than this. Ah, but what is quote 8.3? Is 8 less than 3? No, so it's what?
5, 3.
Quote 5.3 plus 1, and then plus this one. So it's quote 5.3 plus 1, and then plus this one, and etc. So, now watch. The code just almost writes itself after we see that. Yeah? So what is the quote? So tell me, what is, so it's defined quote ND. So now, what's our base case? Okay.
Parentheses less than in
Parentheses, if, parentheses, less than ND, then in that case, what is it?
the 0.
0. Otherwise, let's scroll down here.
Parentheses
Otherwise, let's see,
plus space 1
plus space 1,
space parentheses quote,
space parentheses quote, excellent, excellente, okay, quote,
space parentheses
parentheses minus
minus ND,
ND, yes,
parentheses space D,
D. Yeah, and then when we close that out, it's, now you can see what's highlighted there. When we close that out, it's 1 plus that quantity, right? It's what we return if n is less than d. Is everybody clear on that? So now we can just close out all the parentheses. Is everybody good? So let's do paren, 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 boom. And now we'll run this. And so now we'll do, so let's do, let's see if it works. We'll do quote 11.3, and that's 3, and then quote 10.3, and that's 3, and quote 9.3, and that's 3. But now, quote 8.3, and that's 2. And of course, it goes all the way down to quote 0.3, which is 0. And now, what would happen if I did this? What would happen if I did that? Actually, I don't think I want to do it. Have you ever done, huh? Do you think? Shall I try it?
Wouldn't it just be 0?
What, -1? What's the problem? Oh, it would be 0.
Because-
It would be 0. I guess it wouldn't crash because this is less than, not equals. Yeah, I think that's, yeah, it will be 0. Wait a minute. That doesn't look right.
The problem is if the quotient and I don't know what the D's, or, the problem is if N and D are both negative,
It should be positive.
it should be positive.
Yeah. In other words, if I did quote here, if we did this, QUOT, negative 11, negative 3, that should be positive. That should be 3. Are you with me? So we need to modify this so that it works with negative numbers. Does everybody see what we're saying here?
Is there an or?
Yes.
No. Well, I mean, yes, there is. I lied. But before we do the if n is less than d, what should we do? If d, first of all, let's check this. First of all, let's check if d is less than 0, right? So now tell me, if, watch this, less than d0, if d is less than 0, then what should we return? See, like here, what we should do, here, let me show you. I'm not sure if quotient works this way. Let's do quotient 11, negative 3. We should return negative 3. And furthermore, quotient negative 11, 3 should return negative 3. But then what should quotient negative 11, negative 3 return? 3. So how can we make this? So what should happen if d is less than 0? What should we return? Oh, come on.
Do you need another if to find out if n is negative also?
Well, but before we do that other if, I think we can do something now.
Negative 1 times quotient.
Yeah, the negation of it.
Yeah.
So look, you guys remember how this worked? Look, remember how this worked? Remember how negative, what's negative? Negative 7. Remember what this does? What does that return? 7. So that's the negation. So what should this return? Come on. If less than d0, what should it return? You mean
D.
negative n? How do we write this? Parentheses,
Negative
negate, the negation of what?
D.
Of the quote, so, but now do I put, okay, parentheses, okay, what? Quote, and now, instead of returning the negative, so we return the negative of quote what?
And
And now the what?
parentheses negative.
Yeah, we can't just say the negative of d, we have to say what? Parentheses, the negation of d. All right, is everybody clear on this? Now, let me see if I want one more. Yes, okay. So that's what we're going to return if d is less than 0. And now, at this point, we are guaranteed that when we get to this point, yeah, what are we? Now what do we have to check? Otherwise, what do we have to do? If what? Less than n0 what? Oh, yeah, okay, enter. All right, what? Yeah. So we do what? So what do we return? What do we return in this case?
Same thing except with negative n.
Okay, so tell me what to type.
Negative
The negation of
parentheses quote n.
quote n.
Oh no, parentheses.
Oh, sorry, quote parentheses quote Now we do what? We negate n and what? D, all right. And at this point, what are we guaranteed? What are we guaranteed at this point? At this point, we're guaranteed that they're both positive. So now what can we do?
Before we have before.
What we had before, but what do we have before?
If n is less than d.
If, so now what? Less than
n d.
n d, what? Oh, this is good. You guys are good coders here. Come on. So what? Parentheses. What was it? Yeah, it was plus, it was one, it was, remember we had, it was the 1 plus, right? So what was it? Oops, so it's what? It's plus 1. Oh, sorry, you're right. If n is less than d, it was 0. Yeah, sorry, my mistake. It's 0, otherwise what? Parentheses, what? Plus 1 and what? Quote, now what? Minus n, well, it was d, wasn't it? D, okay, d, and now we're adding, we close that out, and then we have to add that to, oh no, that's just what?
It's been added to 1.
It's been added, yeah. So now we just close it out, is that right? No, we need the d. Right, we need the d, is that right? To add the 1 to. Oh, no, that was wrong. Yeah, it's, the d is here. So not, because quote takes two parameters, right? So those are the 2 parameters for quote. Is everybody with me? Boy, I almost made a mistake there. Boom, 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 boom. All right, here we go. Quote 11:3. Quote negative 11:3. Quote 11 negative 3. Quote negative 11, oops, negative 11, negative 3. Boom, boom, positive. Now look how this thing, I mean, can you guys visualize what the execution path is for this? It's actually probably not a good thing to think about this in too much detail or your head will spin. But what happened when we did this quote negative 11, negative 3? What happened? Let's try to trace what happened here. When we did this, what did it do? First it called itself right here, right? Mm-hmm. And then so it's doing this. So then it's oh, d is less than 0 is true. So what does it do? It calls this. But how does it call this? It evaluates this. And so this negative d returns what? This negative d in this particular example returns what?
3.
Returns 3. So now it's going to call quote negative 11:3. But before it can negate that, it calls this, right? So it goes up here. Are you with me? And now what happens? It's calling it with, what's it calling it with? 11 negative 3. So then it gets past this test, but then it gets to this test. And then, so then it gets called again. And then finally, and then it calls itself repeatedly with them being positive until it gets the right one, and then it goes all the way back and boom, it gives you the right, it gives us that. Now, what do we notice about this? This nesting is really hairy, but check this out. We're going to look at this at the beginning of class next time. There is, in scheme, a condition, COND function. And what we're going to do next time is we'll see that there's a way to do this without all that hairy nesting. And so what happens is it won't be, so the if won't just keep going to the right. So with the condition, So look at how the condition works. The key word is COND instead of if. You see what I mean? And so the way it works is it's a list. See how these parameters work? So here is a list, and here is a list, and here is a list, and here is a list. And each one of these lists has a what? Condition, expression, condition, expression, condition, expression. And then there's another keyword called else. And so we'll be able to translate this. We will be able to rewrite it in a lot cleaner way with the COND, the condition function. And we do meet tomorrow, right? All right, very good. And we don't have any homework, though, do we?
Not for tomorrow.
When's our next homework?
I think it's
Monday, or
Well, Monday we have a holiday.
yeah.
Is it Tuesday or Thursday?
I don't think it's Tuesday.
I don't even remember.
Remember?
Well, whatever.
Yeah.
All right, we can look it up. Oh, it's not due till Thursday. Okay, good. All right, see you next time.